Good afternoon, everyone. Welcome back to E304. Today we're going to continue our discussion of quantized vibrations, and specifically we'll be talking about phonons. So last lecture we started discussing, we continued discussing this model of the interaction between two bonded atoms as two masses connected by a spring. And we derive the allowed energy levels of the system, and we saw that they were quantized. So we talked about the two bonded atoms that form a nanoscale oscillator, like two balls on a spring. The energy of the oscillator, we found that it was quantized, so only certain energy levels were allowed, and those certain energy levels were given by this equation here, where we saw that the separation between energy levels had to do with this HFN quanta, so to speak. The energy difference between the two levels is always fixed, again, so it's always HFN, where Fn is that natural frequency of vibration. So we have a name for these quanta, these HFN bits of energy, and these are called phonons. Just the same as photons are quanta of optical energy, phonons are quanta of vibrational energy. Phonons are important in sound and heat, electrical conduction. In insulators and semiconductors, they are what carry heat through lattices and structures, whereas in metals, it's electrons that do that conduction. So let's talk a little bit more about these lattice vibrations, these phonons, and what they do. So we know that two atoms bonded together can be modeled as two masses on springs. Well, if you have many masses on springs connected together, forming a lattice or a solid, and we know all crystalline solids are made up of these atoms that are bonded together, and each bond can be modeled by one of these springs. Well, we might imagine that the vibration in this lattice can propagate throughout. So you can imagine that if we have some energy expanded here in one atom, it compresses that bond or that spring and transfers that energy to the second atom. And this spring is now elongated, and the next bond or the next spring is compressed. And then that spring elongates and compresses the next one up, and so on and so forth. So energy is transferred through these lattices as vibrations, as phonons. Okay? So phonons can only be present in solid materials, obviously, because the energy has to transfer as vibration from one solid atom to the next. And since all atoms in a crystal lattice are held together by bonds that are similar to springs, these vibrations can propagate and be carried through the atom or the structure. Okay. So what it looks like at the end of the day is that there's these phonons are propagated through structures as waves. So we can see that if you look at atoms that are next to each other, when the separation between the atoms is the lattice separation d, then if the first atom is at its most extended position and the next atom down is at its most constricted position, these are about as far apart from each other as they can be, and so the minimum wavelength that can propagate through this lattice is 2d, so twice the lattice constant, because of course one full wave, is from one peak to the next in the sinusoidal function, so it's a length of 2d. So that's the minimum wavelength that a phonon can have. So it can have greater wavelengths, and those are dependent on the quantum number n, Okay, so if L is the length of the crystal lattice, and N is the quantum number, so N is the quantum number, okay, this lambda n is expressed as lambda n is equal to 2L over n. Now the maximum wavelength that the phonon can have is when n is equal to 1, and that'll be 2L, so twice the length of the lattice. Okay, for the lattice doesn't have any phonons at n is equal to 0. Okay, so n here in the denominator must be at least 1. So if we have crystal lattices that are composed of different types of material, for instance, if you have something like NaCl, salt, we know that's made up of chlorine ions and sodium ions, and they're interspersed in this crystal lattice. So the bonds occur between Cl and Na ions here. So in one dimension we see a chain that's 1 negative, 1 positive, 1 negative, 1 positive. Well, in this case, these types of crystals can have different types of frequencies or different types of phonons. So they can have an acoustical mode and an optical mode. So the lower frequency phonons are called acoustical phonons, and they can carry sound waves. The optical phonons can be excited by electromagnetic radiation, and these are high frequency. So I hope you can see the difference between these is that in this case, the negative and positive ions sort of vibrate in sync with each other, or in the same direction, whereas here the positive ions and the negative ions are vibrating in opposite directions.